Thank you. You said 1098, right? Thank you. You too.
Okay, alrighty. Let's move into section 9.2 today. Same thing that we did on Tuesday, just now with means instead of proportions. Okay. Okay, hypothesis testing for means. Okay. Objectives, write the null hypothesis and alternative for means. Okay. Write the null and alternative. Red pen here. Okay, null and alternative. Okay, check the conditions for the hypothesis test for means. Check conditions. Okay, and this is going to be the same conditions that we had for the confidence interval for means. Okay, condition is my sample size, okay, greater than or equal to 30. Okay, that's the condition that I'm looking for. Is it a large enough sample? Okay, perform a one sample t-test. That's what we're going to perform, is a one sample t-test. We're going to see how we do that on the calculator and how we would do that in StatCrunch. We want to find our p-value, and we want to compare that p-value to a significance level. Most of the time, that significance level is 0.05. If it's less than 0.05, we reject the null. If it's greater than 0.05, then we do not reject. We fail to reject. Okay, t versus z. When do we use t? When do we use z? Well, we use t when we're talking about a mean, and we use z when we're talking about a proportion. Okay, so the sample for a proportion was p hat. We saw that to be p hat. And the standard deviation we saw could be calculated. Okay, standard deviation can be calculated and known. Okay, we can know the standard deviation. Okay, and that was calculated. Okay, we use z. Okay, z normal with mean 0 and standard deviation of 1. Okay, population mean. Now we're going to shift gears and talk about the population mean. Okay, a hypothesis test for means. Okay, the sample mean is X bar. Okay, X bar is the sample mean. And the standard deviation of population is almost always unknown. Okay, it's almost always unknown, the population one. Now the sample one we can find, which is S, but the population standard deviation, or sigma, okay, is unknown. Okay, sigma is unknown. Okay, 5 steps to a hypothesis test. This is exactly the same thing that we did before. Okay, the null hypothesis H sub 0, the claim that we assume will be true, it always has the equal sign. The alternative hypothesis, often what we will try to show, if the null hypothesis is rejected, then we accept the alternative. It has a less than, greater than, or not equal sign depending upon what is being asked. If what's being asked is, you know, is the proportion or is the mean greater than, then we use the greater than symbol. If it's less, okay, then, okay, if it's different or changed, sometimes we use the word changed, okay, is different. Okay, I'll put changed under here as well. Have things changed. All we're looking for is a change. We don't know if it's a positive change or a negative change. Okay, just it's changed. Let me test my speed. Thank you. Yes, there we go. Okay, finish. Okay, tips. Always use parameter notation. Okay, do not use statistic notation in your hypotheses. Okay, number 2, think about the alternative. Are we interested in one direction only, or just showing that a difference has occurred? Okay, which one do we want? Okay, we use P naught and mu naught to represent the values in our null hypothesis. Today we're going to focus on mu naught. Okay. Okay, example 1. From the data collected this year about the number of years of service an employee has at retirement within a certain large company, we obtained the summary statistics. The number N is the number of people that were interviewed. X bar was the average number of years that they were at the company. And the standard deviation, the sample standard deviation, was 11.1. Test the claim that the mean number of years of service at retirement is 25 years. So the claim is that it's 25 years. So the null hypothesis, or H sub 0, is that mu is equal to 25. It's always equal to our claim. The alternative, okay, what's the alternative here? It says, test the claim that the mean number of years of service at retirement is 25 years. Well, it could be over 25, or it could be under 25. So we just want to know if it's not 25. So we don't know if we're looking for above or below. So we just want to know, has this thing changed? And so we get mu is not equal to 25. That's the hypothesis there. Okay. Okay, the run times for 20 participants at a local 5K race was 29.2 minutes. This is my N. X bar is 29.2 with a standard deviation of 5.7. Is there evidence that the true mean runtime for all the participants was below 30 minutes? Okay, and mean, we're looking for a mean. It'll either say mean or average, which again tells me that I'm looking for the average or mu and not a proportion. So HO, mu is equal to something. HA, mu is, in this case, less than, below is the key word there, less than 30. And so my mu would be equals 30. Okay, for my alternative, or for my null, for my null hypothesis. Okay, so this is the null. This is the alternative. Okay. Now, how would we calculate the statistic and get our p-value? Well, we're going to use the t statistic, which is right here. Okay, we have x bar, which is our sample mean, minus the population mean, what we're testing against. Okay, this mu sub 0 is what we're testing against, all over our sample standard deviation divided by the square root of n. This is our standard error. Okay, standard error for means. Okay, so that's the standard error for means. This is the number of means that I am working with. Okay, so my sample size. Okay, step 4. Okay, the p-value is a probability. Okay, it must be between 0 and 1. P-value is the probability of obtaining our result. Okay, or one more extreme. Given that H is true, if we have a really small probability that our null is true, then we would have to reject the null. The smaller the p-value, the more convincing our evidence is. Our evidence is that our null hypothesis is false, i.e. smaller than our alpha level of significance. Okay. Okay, let's calculate the t-test statistic and the p-value here. Okay, so how would I calculate my t-test here, my t statistic? T is equal to x bar minus mu, naught, okay, mu naught, all over s over the square root of n, okay? So what's this going to be? Well, okay, we're going to plug in our values here. X bar is 36. What's mu? What's the mu that we're testing against? The mu that we're testing against is 40. So this is going to be minus 40 all over s, which is 3, over the square root of 20. Okay. I'm going to plug this into my calculator. Let me turn my calculator on. I'm going to get 36 minus 40. I'm going to hit enter. Divide that by 3 divided by, I'm going to put a parenthesis because I'm doing multiple fractions, fractions over fractions, over the square root of 20. Okay, I'm going to arrow over and put a close parenthesis, and that gets me okay, -4 divided by 3, yeah, so negative 5.962, all right, 5.963. Okay, and that would be my t statistic. Okay. Okay, so how would I find my p-value? Well, my p-value is going to be determined based on, okay, based on what my hypothesis is. I'm saying that I want to compare this to 40, my mu of 40, right? Okay, and so we would say that that's our 0 mark, basically. Okay, that 40 is our 0 mark. We turn this into a standard t, okay? And we want to be down here, okay, at negative 0.5963. We want to be less than, okay, so this is one-tailed. So we want to know what's the probability of being less than, okay, less than or equal to negative 0.5963. Okay, so in order to do this, I have to use the TCDF. I want to do a TCDF here. And with a T distribution, you have to take into account your degrees of freedom. Okay. So with n equaling 20, my degrees of freedom is going to be 19. So I'm going to go to second vars. I'm going to go to TCDF, not normal CDF. Normal CDF is for z's. TCDF, I'm going to have the lower be negative infinity. I'm going to have the upper be negative negative 5, not negative point. Okay, it's negative 5.963. 5.963. Degrees of freedom is 19. 19, it's n minus 1. Okay, and then let's paste that. And I'm getting a very small number. My p-value was equal to 0.000, okay, 5 zeros, and then a 49, we'll say, 49. So extremely small p-value. Okay, so in this case, okay, is mu 40? Okay, is mu 40 going to be equal to, is that going to be my claim that I'm going to go with? Am I going to accept HO or am I going to reject HO? Well, if we were comparing this against 0.05, this p-value is much less than 0.05, and so it's a very, very tiny probability that HO is true. Remember, the p-value is the probability that the null is true. And so the probability that the null is true is in the millionths. 1, 2, 3, 4, 5, 6. Yeah, it's like 1 in 500,000 that you would ever get, you know, this to be your 36 to be correct, with mu being 40, given that your standard deviation is only 3. Okay, and so we would reject the null and we would accept the alternative meaning that this is in fact less. Okay, so, and then we don't know what the scenario is here, so we can't name a formal conclusion. Okay, we'll leave that for the next examples. Okay, what about the next one here? What about the next t-score? How could I get a t-score for the next value here? Okay, well, let's do the same thing. X minus mu, x bar minus mu over s over the square root of n. Okay, well, what's x bar? X bar is 3.1 minus mu, which is 2.5, all over s, which is 0.3, over the square root of 50. Okay. So again, I'm going to plug this into my calculator. Okay. 3.1 minus 2.5. Okay. Divided by parentheses 0.3 divided by the square root of 50. Okay, and I get this to be about t is equal to 14.14. That's really big. Okay, this is a two-tailed test. This is a two-tailed test because it's not equal. Okay, it's a two-tailed test, which means, okay, that if I were to try to get my p-value on its own, I would have to split this into two tails. I'd have to split it into a lower tail and an upper tail. And this would be at 14.14. This would be at negative 14.14, right? And so I'd want the probability that the area is either below negative 14.14 or above 14.14. So what I can do is I can find this area here, the lower area, and then I can double it, okay, to get my p-value. Okay, in this case, n is equal to 50, which means my degrees of freedom is equal to 49. And I can go back to my TCDF, second vars, go down to my distribution, which is the T, number 6, TCDF. And in this case, instead of negative 5.963, I'm going to go negative 14.14. This is going to be extremely small. Okay, and then the degrees of freedom is 50. Okay, and I'm going to paste that. And I'm going to hit enter, and it essentially says, look, it's 0.
Wasn't the degrees of freedom 49?
Oh, did I not put it in correctly?
You said 50.
Oh, I'm sorry. Yeah, it is 49. It really doesn't matter in this case, but yeah, it is 50. Or sorry, it is 49. Thank you. Okay, it's 49, and it's basically 0. The calculator can't even calculate how small this is. It's extremely tiny. And so we say, oh, the p-value is essentially 0, which is always less than whatever significance value I could come up with. So in this case, I'm going to reject. Okay, and this area is 0, which means that this area is essentially 0. So if I double 0, I still get 0, right? If I go 2 times my answer, 0, I still get 0. So I would have to double this if this came out to something other than 0. I would have to double it, but in this case, we're all good. Okay. Okay, so again, I would reject, and I would say, yeah, no, it's not equal to 2.5 anymore. Your claim is bogus. Okay, in both of these, I would reject the null. In the first one, I'd say, no, your claim that it's 40 is wrong. Okay, it's less than 40. And in the other, in the one that we just did, we'd say that your claim of 2.5 is wrong. Okay, the alternative is true, which is that it's not 2.5. Okay. Okay, how would we do the t-test on the calculator without having to run any of these statistics on our own? Okay, if we want to do a t-test on the calculator, okay, it's a one sample t-test, okay, or just called on the calculator, it's called t-test. Okay, it's just a t-test. One sample t-test is just t-test. Okay, I'll do it on the calculator first, and then we'll go to StatCrunch, and I'll do it on StatCrunch. Okay, so let's take the last one here. Well, I don't like the last one because it comes out to 0. Let's take the one before, so we can verify all these numbers. Let's take where the hypothesis is mu is equal to 40, and let's have the calculator do all the heavy lifting for us. So I'm going to go to stats, okay, and I'm going to go to tests. So stat, tests, and then number 2 is t-test, okay? So t-test, number 2. Okay, so I'm going to arrow down to number 2 here and go t-test, and it says, okay, what do you want to use? I want to use my stats to get my t-test. And they're saying, okay, well, what's your mu naught? What's mu naught going to be? What's your hypothesis mu? Your hypothesis mean? What are we claiming it to be? Well, I'm claiming that it's 2.5. No, I'm claiming that it's 40. I want to use the first one here. I'm claiming that it's 40. Okay, and then what are we getting as our sample? Our sample X bar, well, that's 36, right? Okay, what's our sample standard deviation? 3. And how many in the sample? 20. And what are we wanting to do? Less than, not equal to, greater than? I'm going to do not equal to, so I arrow over and I hit enter. Okay, I'm sorry, I want it to be less than. Okay, so I hit enter and then I just hit calculate. Okay, and what does that do? Well, it does the t score for me. That's nice. Okay, and it comes out with my p-value, and I didn't even have to worry about the degrees of freedom, right? Because the calculator calculates the degrees of freedom based on the sample size all by itself. So I didn't have to draw a chart. I didn't have to do anything. The calculator did it for me. Okay, so how would we do this on StatCrunch? For those of you that are working with StatCrunch, let's pull up StatCrunch here. It'll come up. Okay, any day now. Okay, let me sign in. Okay, so we want to do a t-test, t-hypothesis test, okay, on StatCrunch. So let's go to stat. Okay, let's go to t-stats. Let's try that again. Stat, t-stats. Oh my gosh. Stat, t, what the heck? T-stats. Is it going to work? Ooh. Okay, forget it. I'm just going to use my mouse. Okay, t-stats, one sample with summary. Okay, t-stats, one sample with summary. And says, what's our sample mean? Well, our sample mean was 36. Okay, what's our sample standard deviation? It was 3. What's our sample size? It was 20. Okay, what's our mu that we're testing against? Well, I'm testing against a mu of 40. And then are we doing less than, not equal to, or greater than? Yeah, we're gonna do that. Okay, we don't have to worry about the confidence level. That's for a confidence interval. And all we do at this point, we've plugged everything in. We just hit compute. And here we go. It says that the mean is 36. The standard error is 0.67. The degrees of freedom was 19. Already knew that. The t-stat was negative 0.596. Okay, that's what we got before. And what's the p-value here? The p-value is so low that it says it's less than 0.0001. Essentially, it's to this guy, it's essentially 0. Okay, but yeah, is 0.000046 or 49 less than 0.0001? Yeah. Okay, so StatCrunch gives you a little bit less accuracy than the calculator, but for all intents and purposes, we would still reject the null, okay, because it's just so super low. These values are so super low, we would reject the null. Okay, so that's how we would do it on StatCrunch. Okay, let's go through one in its entirety. Let's go through a t-test, okay, in its entirety, all five steps here. Okay, number 1. Okay, we want to define the parameter we're testing, the null and the alternative. It says the run times for 20 participants in a 5K race was X bar equals 29.2. You have a question? Oh, okay, thanks. Okay, with a standard deviation of S equals 5.67, is there evidence that the true mean runtime for all the participants is below 30 minutes? Okay, so we're testing against a true mean of 30 minutes. Cool, thanks, Jared. Okay, so what's our null hypothesis? What's our null hypothesis in this case? We're going to be testing against 30. We're going to be testing against 29.2. What are we? Is it mean, proportion? Okay, what's the parameter that we're going to be using? Well, it's u equals. Remember, the null is always equal. Equals what? Equals. We're testing against the claim that this is 30 minutes, right? So mu is equal to 30 minutes. What's the alternative? Mu is less than, right? Because of the word below here. Mu is less than 30 minutes. Okay, that's step 1. What's the test that we're going to be using? Oh, it's a one sample t-test. Okay, one sample t-test. That's what we're going to be using. Number 3, are the requirements met? Is it a large population? Yeah. Is it a random sample? Yeah. Is the sample size, okay, is the sample size bigger than 20? Okay, is the sample size n, sorry, not 20, is n greater than or equal to 20? No. No. Okay, but we will assume in this case that finish times are normally distributed, okay? Or we won't say normally distributed, we'll say that finish times are symmetric. So even though the sample size isn't big enough, we're still going to assume that you're going to have fast people and you're going to have slow people, okay? And then you're going to have a bunch of people in the middle. So we're going to assume that this will follow some sort of t distribution, some sort of normal distribution, okay? Not normal distribution, t distribution. And so we're going to continue on as if the sample size was larger than 30, okay? We're going to assume that in this scenario, okay, people people do are going to finish with some sort of symmetry. Okay. Okay. Number 4. Okay, we could calculate our test statistic. Okay, so we would calculate what t is equal to and our p-value. Let's have the calculator do this for us. I don't want to go through all the labor of trying to calculate all this on my own. Why is my calculator not wanting to run? Let's reboot that. Things get slow when I pull up the browser. So there we go. Okay, so let's go back to stat, tests, t-test. Okay, and we want stats. So what are we testing against? I'm testing against 30, mu of 30. What's the x bar that they give me? Well, the x bar they give me is 29.2. Okay, so 29.2. Okay, for a 5K. That sounds about right. Half hour. That's pretty fast. That's about good. That's about average. Okay, 29.2. Okay, S, the standard deviation of 5.67. Okay, and in this case, N is 20. Okay, 20 participants. And we're testing against it being less than. So I'm going to leave that as less than. Okay, is there evidence that the true mean runtime is below 30 minutes? I'm going to calculate, and it says, well, look, your t-score is negative 0.631. I'll just put 0.631 or 0.6310. That's what that rounds to. Okay. For a p-value, what's my p-value? My p-value is 0.268. 0.268. Okay, so we're going to let alpha, okay, we're going to let alpha be 0.05. So what's my conclusion here? What's my conclusion? My conclusion is that since 0.268 is greater than 0.05, what happens? Well, do I reject or do I fail to reject? Okay, do I reject or fail to reject?
Fail to reject.
Yeah, we fail to reject, exactly. Okay. Hello, come back. Go away. Go away. Go away. Okay, yeah, we're going to fail to reject. So we're going to assume that this guy is true. We have not proven him false. And we're going to fail to reject. We're going to say, since this is greater than this, there is not sufficient evidence to suggest that mean runtimes were below 30 minutes. Okay, so that's it. That's my conclusion. There is not sufficient or insufficient, maybe we could say insufficient evidence to suggest that mean runtimes for the 5K was below 30 minutes. Okay, so that's.
I have a question.
Sure.
Why are we not using for the greater or lesson, why are we not using 30? Like, why do we use the 0.05?
Oh, that's my significance level that I'm testing my
Okay.
p-value against. Okay, it's the same thing that we did with the proportions, where we were testing the p-value against a significance level. So we're not sure enough. Okay, we're not 95% certain that it can't be the true mean. So we don't reject. We fail to reject.
Okay.
Okay, example 4. Okay, insurance companies track life expectancy information to assist in determining the cost of life insurance policies. The insurance company knows last year the life expectancy of its policyholders was 77 years. Okay. They want to know if their clients this year have a longer life expectancy on average. Okay, cool. Okay, so the company randomly samples some of the recently paid policies to see if the mean life expectancy of policyholders has increased. The insurance company will only change their premium structure if there is evidence that people who buy their policies are living longer than before. Okay, so I guess this is the age at which these people died. So, in which they paid out. Kind of a morbid example. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 20 people here. Okay, so I'm going to use the data feature of my calculator. Okay, it says, does the sample indicate that the insurance company should change its premiums because life expectancy has increased? Test an appropriate hypothesis and state your conclusion. They give me a histogram there. That's all well and good. We don't really need it. We're going to use an alpha of 0.05 to test against. We want our hypothesis. Okay, what's our null hypothesis? Is that the average is equal to 77, that it hasn't changed. Okay, what's the alternative? The alternative is that we want to make sure that we want to see if people are living longer, which means we're going to be out money. Okay, mu is equal to, is greater than, we want to see if they're living longer, greater than 78. Okay, so we can give a benefit to the people who are buying. Okay.
Wouldn't that be 77 as well?
Oh yeah, 77, thank you. I don't know why I wrote that. Thank you, yes. Greater than 77.
And if they live longer, doesn't it make more money? Because they collect more premiums, maybe 2, 3 years.
Yeah, they would.
Okay.
Yeah, exactly.
Yeah,
Yeah,
okay.
you're right.
Just double checking.
Yeah. So if they live longer, then the insurance company makes more money. If they live shorter, then they're out money. Exactly. Okay, number 2, what are we going to use? We're going to do a t-test. Okay, that's the test that we're going to run. Is the t-test. Number 3, okay, is, we're going to assume that it's a large population. We're going to assume that it's a random sample. And N here is.
I have a quick question.
Sure.
Is t-test for means and z-test for proportions?
Yeah, but you don't. But if you're running with the calculator, you don't do a z-test. You only do a z-test when you know that the population is normal. Okay, you only do a z-test
Okay.
when you know what the population standard deviation is. And that's almost
Oh,
all
I see.
not known to you. And then you don't even run a z-test. What you run is, if you have a proportion, you have to do what's called a one prop z-test. They're different. So you can see that number one here.
I'm using StatCrunch, so I'm not really using my calculator, but
Yeah, so
I was just confused when to use t-test.
sure. So you're going to want to use the proportions part and the t part. You never want to use the z part or the normal part. Okay.
Oh, okay.
You either
Yes.
use number two, which is the t-test here, or you use the one prop z-test. Now I exited out of StatCrunch just because having the internet up slows down my connection.
Yeah, no, that's fine.
Yeah, but it's the same thing that we did for confidence intervals. Okay, so we never really use this z-test.
Got it. Okay.
Sure.
Thank you.
Sure. Okay, so n here is that greater than or equal to 30? No, again, it's no, but from the histogram, we can see that the histogram is fairly symmetric. That's symmetric. Okay, so we're going to go ahead and run a t-test. Okay, so we're going to again have the calculator calculate the t-score and the p-value. So I'm going to go to test, t-test. Okay, in this case, we're going to go to data. Okay, and what I'm going to want to do is plug in all of this data where? Into L1. So I'm going to go stat, edit. Okay, and I want to edit L1 here. So I'm going to go up and I'm going to clear it. Do you have a question? Okay, sure. Sounds good. Yeah, I'll do that afterward. Okay, so I clear this L1 and then I'm going to put in my values. I'm going to put in 86, 75, 83, 84, 81, 77, 78, 79, 79, 81, 76, 85, 70, 76, 79, 81, 73, 74, 72, and 83. Nope, 83. Okay. So now I'm going to exit out of this, go back to stat, go back to my test that I left off at. I want to do the t-test, right? T-test. Okay. Using the data, how many's in my, what am
20
I?
in your samples, 20.
Yeah, my sample size is 20. Okay. My what I'm testing against is 77. My population mean that I'm testing against is 77. All of the data is in list 1. Okay, frequency 1 is fine. This means I'm going to be using my data once. And then greater than 77 is what I want to test against. So I can move over the greater than symbol, I hit enter, and then I hit calculate. Okay, and t comes out to be, okay, 1.598. And my p-value is 0.063. Okay. Okay, let's do this on StatCrunch real quick. I'll get rid of the calculator. Okay, let's go to StatCrunch. Oh, that's nice. It kept me logged in. That's good. Wonders never cease. Okay, and then we're going to go stat, tstats, stat, tstat, tstat. Let's try it again. Stat, tstat, one sample. This time it's with data. With data. Oh, I got to put in my data first. Okay. So let me type in my data real quick. Okay. So the data was 86, 75, 83, 84, 81, 77, 78, 79, 79, and 81, 76, 85, 70, 76, 79, 81, 73, 74, 72, and 83. Okay, and then I'm going to check this just to make sure. 86, 75, 83, 84, 81, 77, 78, 79, 79, 81, 76, 85, 70, 76, 79, 81, 73, 74. Oops. Okay, that goes really fast. Okay, 73, 74, 72, 83. There we go. Okay, that works. So now I'm going to go to stat, tstats, one sample with data this time, with data. What's the column that I want to use? This column here, var1. Okay, that's good. What do I want to test against? I want to test against 77. And I want to make it greater than this time. Okay, and we just hit compute down here. It should say compute. If I bring this up, it's hard to see, but it does say compute. And we just click compute error. What is this? Oh, you must select the column there. We select the column. Okay, and just hit compute. And it gives me the exact same t-stat that we had before, 1.598, and the same p-value of 0.0632. Okay. So now we're going to go back and write our conclusion. Okay. Again, what is our conclusion here? Okay. Well, our conclusion, okay, is that since, do you have a question? Okay. Oh, sure. You're welcome. Okay. Since, okay, 0.063 is greater than 0.05, which is our significance level. Okay, 0.05 that we chose. Since 0.063 is greater than 0.065, there is insufficient. Again, we're gonna keep the null and we're gonna reject the alternative. We keep our hoe this time. Okay, keep them hoes. Okay, so since 0.063 is greater than 0.05, there is insufficient evidence to suggest that life expectancy has increased beyond 77 years old. Boom. Okay. Okay, any question on this? Any question on the anything we've covered so far? Okay, this is it for the notes for today. I'm gonna hang around for the next hour and field questions from any of the homework so far. Okay, so if you have homework questions, feel free to stay. Okay, you're welcome. Okay, if you don't have homework questions and you're just going to work on the homework on your own, you are free to leave. You're free to abandon ship at this point. Okay, you're always free to come back in if you get stuck. Okay, again, I'll remind you that there is free tutoring Monday, Wednesday, and Thursdays. There's also free tutoring through the Math Lab Monday through Friday, okay, until 9 o'clock. Okay, thank you. Have a great week. You too. Thank you. You have a great weekend as well. Okay, so I'm going to enjoy the hot sun from my balcony. That's about all I can do. And maybe I'll put a basketball hoop on my roof or something so I can play basketball. So I don't know. See what happens. Thanks. Okay. So yeah, that's it. That's it for today, for the notes. Okay, so I'm going to create a couple of breakout rooms here for those of you who have questions. Bye. Okay, stop the sharing. Stop share. And I want to stop the recording as well. Stop the recording.